Most drivers along Texas's back highways never slow for the dusty road cuts slashing through hill country granite. But just feet from the shoulder, thin quartz ribbons, some only a few centimeters wide, snake through fractured host rock, hinting at what early prospectors overlooked. These inconspicuous veins, exposed by road construction decades ago, have begun attracting a new wave of amateur geologists and serious prospectors who understand that in Central Texas, quartz isn't just quartz. It's often the opening line in a gold-bearing story. The Llano Uplift region, which includes parts of Llano, Mason, and Gillespie counties, contains some of the oldest exposed rocks in Texas. These Precambrian granites and schists were fractured during ancient tectonic shifts, forming conduits that hydrothermal fluids later filled with quartz, sulfides, and, occasionally, native gold. However, unlike the dramatic quartz bonanzas of California or Colorado, Texas's gold hides in thinner stringers and low-yield zones, easily dismissed unless you know what to look for. The key indicator at many of these overlooked road cuts is not just the quartz itself, but what surrounds it. In several re-examined sites west of Llano, weathered road faces show oxidized iron staining, rusty reds and oranges, alongside thin white veins. While iron staining alone isn't diagnostic, in Texas, it often correlates with past hydrothermal activity, and where there's iron, there may have once been sulfides, and with them gold. Prospectors use simple field tests, like scratching the vein with a pocket knife or inspecting under a loupe, to look for signs of brecciation, broken host rock, subtle pyrite cubes, or a greasy, milky quartz texture. The true missed opportunity lies in the scale. While each cut may only yield a handful of samples, there are hundreds of such cuts scattered across the hill country, each a potential vector into a forgotten hydrothermal system. By building a grid of these locations, prospectors can triangulate likely source veins and downstream alluvial concentrations. It's not just one lucky hit. It's a replicable method for tracing Texas gold back to its bedrock origin. But knowing where quartz is exposed is only half the equation. The next step is being able to recognize what makes some quartz worth sampling and others worth walking past. What exactly distinguishes gold-associated quartz from the ordinary? The answer isn't in color alone. It's in luster, density, and habit. The critical difference between ordinary quartz and gold-bearing quartz often lies in a subtle surface property that most overlook: the luster. While common quartz reflects light with a clean, glassy shine, hydrothermal quartz associated with gold tends to display a duller, greasy or waxy sheen, especially when fractured or weathered. Under angled sunlight or a high-lumen flashlight, this difference becomes more apparent. That greasy luster signals rapid precipitation from mineral-rich fluids, which often carry not only silica, but fine particles of gold and sulfides. Experienced Texas prospectors don't rely on color alone. Instead, they pick up samples and note their weight in hand. Quartz with embedded sulfides or microscopic gold tends to feel denser than expected. For instance, two fist-sized pieces of similar-looking quartz can differ in weight by up to 20%, with a heavier sample often containing iron minerals or metallic inclusions. This tactile density clue becomes second nature with field time and allows quick triage of roadside finds before committing to hauling them. Crystal habit also matters. Gold-associated quartz in Texas rarely appears in clean, six-sided crystals. Instead, it forms as irregular vein fillings within fractures, especially in schist or granite hosts. These veins may be less than 2 inches wide, but extend for several meters, and their margins often show oxidation halos, red, orange, or black discoloration, caused by weathering sulfides like pyrite or arsenopyrite. In road cuts across Mason and Llano counties, some of the richest samples came not from the cleanest-looking quartz, but from these dirty, iron-stained border zones. To avoid wasting time or losing track of promising samples, methodical collection is crucial. Each piece should be labeled by GPS coordinates and stratigraphic position, even if pulled from shallow roadside cuts. Marking bags or using waterproof field tags lets prospectors later correlate surface traits, like luster or staining, with lab or pan results. Many amateurs throw away their best leads by mixing everything into a single bucket. In Texas, gold doesn't appear randomly. It follows structure. And nowhere is that more evident than in the Llano Uplift, where the collision of ancient continental plates left behind a fractured, mineral-rich crust. Here, hydrothermal activity millions of years ago injected superheated fluids into zones of weakness, depositing quartz and, under the right conditions, trace amounts of native gold. Without understanding this structural logic, prospecting becomes guesswork. But with it, each outcrop becomes a potential clue in a broader network. Gold typically forms in epithermal to mesothermal vein systems, medium-depth environments where mineral-laden water deposits both silica and metals. In the Llano region, these systems tend to occur along fault lines, shear zones, or the contact margins of granites and metamorphic rock. Mapping these features, either through geologic maps or direct field observation, is a foundational step. In many cases, quartz veining occurs along northeast-southwest trending fractures, consistent with regional tectonics. And where these veins cross certain iron-rich schists or amphibolites, the conditions become even more favorable for gold deposition. But gold doesn't move alone. It travels in association with sulfur and iron, which means the presence of sulfide minerals like pyrite, chalcopyrite, or arsenopyrite is a strong secondary indicator. In the field, this shows up as rusty staining, weathered pyrite cubes, or even small Gaussian outcrops, oxidized remnants of once metallic zones. In the Enchanted Rock vicinity and extending into Mason County, such zones often appear near low hills or along eroded creek beds where weather has revealed fractured bedrock. These locations become prime sampling targets, especially after storms or seasonal runoff events. Another layer of terrain logic comes from drainage patterns. Gold, being dense and inert, concentrates in specific alluvial settings, particularly on the inside bends of creeks or behind natural obstructions like boulders and tree roots. But in Texas, many gold traces occur not in current watercourses, but in paleochannels, ancient stream beds now buried under sediment or revealed only during low water periods. Identifying these features requires reading topographic subtleties, like terrace levels, gravel deposits, and unnatural linear depressions. These often align with the same faults that carried the original gold-bearing fluids. Yet, even with correct structural understanding, not all quartz veins in Texas will carry gold. Some are sterile, formed during unrelated thermal events or in geochemical environments that excluded gold. That's why smart prospectors overlay structural maps with historical data and field clues, narrowing their focus to those areas where quartz, sulfides, and host rock chemistry align. Still, even the most promising terrain doesn't yield gold immediately. The next challenge is catching the first real indicators, those elusive signs that gold is not only geologically possible, but physically present. And for many, that first proof appears not in bedrock, but in creek sediment, just a swirl away in the bottom of a pan. After weeks of dry heat, a single hill country thunderstorm can transform narrow gullies into torrents, and then, just as quickly, drain them back to gravel and silence. But to the trained eye, what remains behind in these creeks isn't just debris. Flash floods scour overburden and expose pockets of compacted gravel, windows into Texas's ancient fluvial systems, and sometimes into gold itself. In these moments, prospectors with the patience to read sediment patterns gain access to material untouched for decades. Paleoplacer deposits, ancient gold-bearing stream beds now inactive, are often revealed this way. Unlike modern creek channels, paleoplacers may sit meters above current water flow or buried under colluvium. Yet where modern tributaries intersect these older paths, erosion cuts down through the layers, unveiling cemented gravels with unusual density and color. Along tributaries of the Llano River, some of the richest finds have come not from the main channels, but from small side creeks where slope failure or undercutting expose these time-locked strata. Key to recognizing a potential paleoplacer is the composition and compactness of gravels. Ordinary alluvium is loose and varied, but ancient gold-bearing layers often show tight packing, with well-rounded quartz pebbles, red or brown iron staining, and a heavier matrix. Field tests here begin with feel and sight. Does the material resist digging? Does it carry unusually dark or red sediment when panned? Sampling in layers, removing material centimeter by centimeter, can reveal a concentrated paste streak resting on clay or bedrock, often no more than a few inches thick. In certain pockets of Mason and Llano counties, these paleoplacer zones sit just below thin layers of decomposed granite. When concentrated by even minor stream energy, the result is a fine distribution of flour gold. Microscopic flakes visible only under specific panning angles or with contrast aids like black gold pans or colored basins. While this gold is small, it's proof of upstream hydrothermal activity. And more importantly, it can lead to veins or erosion zones that continue uphill. What sets Texas apart is how localized this gold can be. A single gully may yield flakes in 3 meters of creek, but nothing upstream or down. This makes record-keeping essential. GPS pins, photo logs, and marked concentrate bags allow prospectors to return after seasonal shifts or to focus deeper sampling where material proved richest. In high-traffic areas, this can mean beating the seasonal rush by only a few days. Yet even with visible gold, one variable remains constant: the accompanying minerals. Iron-rich sands, manganese-stained gravels, and oxidized sulfide fragments are almost always present with gold in these zones. Identifying and isolating them, especially one in particular, can refine the search even further. Because where there's gold in Texas, there's usually another metallic companion that appears first and louder: pyrite. But not all pyrite is a friend, and some types offer far more than others. It gleams just enough to raise hope, but most beginners throw it out, mistaking it for worthless fool's gold. In central Texas, pyrite does more than mislead. It often marks the front edge of a hydrothermal system that once carried gold. Understanding its forms and associations can spell the difference between a wasted afternoon and a high-probability zone. The trick isn't whether pyrite is present. It's reading how it's present and what it's telling you about the gold that may lie just beyond it. In the Llano Uplift, pyrite tends to occur in two main habits: cubic and massive. Cubic pyrite, especially when found fractured or partially weathered, is a key clue. In multiple reworked sites around Loyal Valley and Catamsey, oxidized pyrite cubes appeared consistently in soil samples taken within 20 meters of productive quartz gold veins. These weather to limonite, an earthy, yellow-brown iron oxide, and often accumulate just above the contact between quartz and schist or amphibolite. When you find these cubes scattered in the soil or trapped in heavies during panning, they are not decoration, they're directional. Prospectors use this signal by following the float, collecting progressively uphill until the cubes disappear. The point at which pyrite concentrations fade can often correspond to the edge of the mineralized zone. In the field, even without lab access, one can test weathered pyrite via streak and acid. Real pyrite leaves a greenish-black streak and resists cold hydrochloric acid, while limonite or other iron oxides may bubble or smear orange. But pyrite isn't the only iron marker. In richer zones, it's often accompanied by magnetite or hematite, each with distinct magnetic and streak properties. A simple field magnet can help isolate these heavies from pan concentrates. More interestingly, in some gold-rich quartz veins in Mason County. Coarse-grained pyrite appears in close proximity to visible gold, a relationship well documented in mesothermal systems. These associations suggest the gold precipitated in the same thermal window, often within narrow pressure temperature thresholds. Yet not all shiny fragments belong to pyrite. Chalcopyrite, a copper-iron sulfide, often appears iridescent and golden in hand sample, but it weathers differently and lacks the cubic form. Its presence, while less directly tied to gold in Texas, still signals a hydrothermal history worth mapping. A hand lens or loupe, 10x, quickly reveals the difference in crystal form and oxidation halo. Some prospectors apply a drop of nitric acid to suspect fragments. Pyrite remains mostly unchanged. Chalcopyrite may release a faint green hue due to dissolved copper. Even limonite, the rust rock dismissed by many, deserves scrutiny. In several cases near Llano, limonite-stained quartz collected from old road cuts tested positive for trace gold after crushing and gravity separation. These samples showed no visible gold, but their geochemical fingerprint matched nearby known veins. In short, iron oxides act as breadcrumb trails, but finding pyrite and limonite is only half the task. Knowing how to isolate and test surrounding materials without water, especially in Texas's long dry spells, is what allows fieldwork to continue even in drought. The next step is adapting to these constraints by using a different kind of sluicing, one that doesn't need a stream. And in Texas, that means dry methods, vacuum tools, and clever use of gravity. Most prospectors wait for rain. The patient ones bring a vacuum. In much of central Texas, where reliable surface water is scarce outside the rainy season, traditional sluicing becomes unfeasible for months on end. But the gold doesn't vanish. It just settles deeper into cracks behind rocks and in fine dust layers that resist casual panning. Those who adapt to dry collection methods, especially in historically productive zones, have begun pulling surprising values from ground others walk past. Dry sluicing in Texas revolves around three essential tactics: concentration by gravity, classification by mesh size, and targeted suction. Instead of relying on flowing water, modern prospectors use small battery-powered vacuums or gas-powered dry vacs to collect dust and gravel from bedrock cracks, under overhangs, or the bases of large boulders in seasonal drainages. These areas, natural gold traps, can retain fine particles for decades. Because gold is up to 19 times denser than surrounding sediments, even a weak slope can concentrate it just a few inches below the surface. Before vacuuming, material is often classified using screens, typically number 20, 0.85 millimeters, or number 30, 0.6 millimeters, to remove large debris and focus on pea-sized fines. Concentrates are stored in sealed bags or buckets, dry, until they can be processed at home with recirculating sluices or blue bowl separators. What matters is not instant results, but preserving the integrity of the layer and ensuring sampling from the right context. One vacuumed crevice might yield 50 grams of material, but if it sits at the downstream lip of a quartz vein outcrop, it's worth 10 times more than a random scoop. Texas prospectors have refined the dry method further by adding visual indicators. They sweep crevices with magnets beforehand to check for magnetite or ilmenite, dense, dark minerals that often co-settle with gold. When present, these magnetics act as proxies for nearby heavies. Another field trick: lightly dampen a pinch of dust to test for fine rust coloration. A strong reddish tone often comes from limonite-rich soil, a common gold companion in the region. In certain drainages near Grit and Pontotoc, documented cases show prospectors recovering over 1.2 grams of gold from just a few hours of dry vac work, mostly from tight, shaded gullies that had never seen water pans. These finds, while modest in weight, consistently contained angular flakes and micronuggets, suggesting local bedrock origin rather than distant transport. It means the gold hasn't traveled far, and the source vein may be uphill waiting. But dry collection isn't foolproof. Lightweight mica, decomposed schist, and even plant material can contaminate concentrates. That's why the next step, panning even trace samples with care, is essential. And while the first specks may seem invisible, those who know what to look for in the bottom of the pan can find gold even when it hides in plain sight. You almost miss it, until the sunlight catches a flash so fine it looks like dust with intent. The first sign of Texas gold in the pan rarely comes as a nugget. Instead, it appears as flour. Fine flakes that cling to the black sands, resisting the swirl of water. To most beginners, it looks like mica, or worse, nothing at all. But those trained in contrast, motion, and patience know that this moment marks the threshold. If flour gold is present, the system is alive, and possibly richer than it appears. Flour gold in Central Texas often ranges between 50 and 200 mesh, 0.3 millimeters to 0.07 millimeters, making it nearly invisible without technique. The pan must be pre-wetted and cleared of lighter material gradually, using a gentle, circular motion that lets the gold settle in the corner crease. Using black or green pans helps, but the real difference comes from lighting. Indirect natural light or a low-angle flashlight reveals gold's telltale flash that doesn't fade when the pan moves. Unlike mica, which sparkles in shifting hues, real gold holds its warm glow regardless of angle. The distribution of flour gold in a pan tells you something deeper about the deposit. A few scattered specks might indicate incidental washdown, but a dense streak, especially near the bottom crease, aligned with magnetite or garnet, signals a consistent upstream source. In Texas's drier climates, where water flow is episodic, even these finds may have remained in place for years, waiting for a careful hand to uncover them. That's why even partial pans must be documented. A test pan with 8 to 10 specks from half a shovel load is significant and worth mapping. Most effective panning in the hill country follows a layer-by-layer approach. Instead of scooping from the surface, skilled prospectors dig down to compacted clay or decomposed bedrock, where heavies naturally settle. Then, they pan material in 1 to 2 cup increments, watching how black sands behave. Gold, being denser than nearly everything else, will drop first, but may hide beneath magnetic minerals. A simple neodymium magnet in a plastic bag can strip magnetite and ilmenite from the pan, clearing the view. This doesn't remove gold, it reveals it. Another tip: swirl water slowly, then tap the side of the pan sharply. Gold will migrate inward, hugging the crease. If a fragment stays still when everything else moves, it's worth inspecting. And while one pan doesn't make a claim, consistent fine gold across multiple test sites begins to form a pattern. That pattern, when overlaid on a terrain map, can point directly toward a source vein. Still, not all quartz in gold-rich drainages is created equal. Some pieces may contain visible inclusions, while others are valuable without showing a trace of gold to the naked eye. In fact, collectors are increasingly interested in a specific type of quartz from Texas that sells well, even when no gold is visible. The key is in its staining, structure, and matrix. And understanding why that quartz pays, even rough, is what separates the casual hunter from the informed prospector. It doesn't sparkle, but it sells. In Central Texas, certain pieces of vein quartz fetch surprising prices from collectors and lapidaries, even without visible gold. What elevates this material isn't flash, but formation. Quartz that formed under hydrothermal pressure, infused with iron, manganese, or copper oxides, often develops complex internal zoning, color banding, and mineral associations that tell a geological story. For those who can recognize it, This character quartz can be just as valuable as small gold finds, and often more abundant. One trait buyers look for is iron-stained quartz. These specimens often exhibit deep orange, red, or brown surface tones from limonite or goethite oxidation, suggesting a history of sulfide decomposition. This staining can be superficial, but when it penetrates fracture planes or outlines brecciation zones, it signals a former hydrothermal pathway. Collectors especially favor pieces with contrasting textures. White quartz veined with rust-red webs or pitted surfaces lined with tiny oxidized vugs. In the field, such quartz appears most often in contact zones between granite and schist or along fault shear margins. On the outskirts of enchanted rock and around the pack saddle schist belt, prospectors have retrieved quartz plates and vein fragments showing hematite blooms and manganese dendrites, fine black fern-like patterns caused by mineral-rich fluid seepage. Even when gold is absent, these patterns elevate the piece's value for display or cabbing. Field recognition of valuable quartz starts with three elements: context, color, and fracture. Context means verifying that the quartz occurs in or near a hydrothermally altered zone, especially near pyrite-bearing veins. Color refers not to brilliance, but to the presence of reds, yellows, blacks, or purples, signs of oxidation or minor mineral inclusion. Fracture matters because conchoidal breaks, brecciation textures, and healed fissures suggest repeated mineral deposition, a positive sign for collectors and geochemists alike. Once collected, these pieces require minimal prep to assess value. A rinse with diluted vinegar can reveal underlying structure, while a loop inspection can identify hematite traces, pyrolusite, or secondary copper staining like chrysocolla or malachite. These add interest and marketability. The most valuable pieces often combine aesthetic complexity with geologic significance. Quartz that not only looks unique, but tells of pressure, heat, and time. Buyers range from private collectors to institutions studying fluid inclusion pathways, and prices vary widely. In recent online auctions, small, 10 to 20 centimeters, slabs of Texas iron-stained quartz with manganese patterns sold for $30 to $120, while more massive chunks with partial pyrite cubes or hematite infill commanded $150 plus. These pieces often trade through regional gem shows or direct-to-buyer social media groups focused on domestic mineral finds. Still, the presence of colorful quartz isn't always a green light. Some minerals mimic iron staining, and certain low-grade material is artificially enhanced to appear oxidized. That's why the next step, discerning real indicators from deceptive lookalikes, is critical. And one of the most common traps comes in glittering form. Minerals like chalcopyrite and mica that dazzle at first glance but collapse under scrutiny. It glints, it flashes, it fools thousands. Chalcopyrite, often mistaken for gold in Texas outcrops, can be so convincingly lustrous that even seasoned rockhounds pause. Its brassy tones and iridescent overtones appear in crushed quartz, stream concentrates, and even weathered schist. But unlike gold, it betrays itself under pressure. To prospectors chasing real value, chalcopyrite is not just a nuisance. It's a false positive that can mislead entire sampling campaigns if not identified early. The confusion begins in oxidized zones where hydrothermal activity once pushed mineral-rich fluids through fractured host rock. In these systems, chalcopyrite, CuF2, often precipitates alongside pyrite and quartz, especially in mid-temperature environments. Visually, its golden hue and flashy rainbow tarnish can mimic gold, but its behavior under test conditions differs completely. Real gold is malleable. Chalcopyrite is brittle. In the field, a quick crush test with the back of a knife or rock hammer will shatter chalcopyrite into angular fragments, often revealing a dark green or bluish interior. One of the most common field traps occurs in mica-rich schists, common across the Llano and pack saddle formations. Fine flakes of biotite or muscovite embedded in weathered rock surfaces catch light and create a shimmering illusion. Under motion, these specks dance, shifting color and fading out at certain angles. In contrast, gold maintains a consistent warm glow regardless of viewing direction. The motion test, swirling material in a gold pan while watching for fixed versus flickering glints, can eliminate most mica confusions within seconds. Field tools can speed up confirmation. A simple hardness test using a steel knife, 5.5 on Mohs scale, reveals that gold, much softer, 2.53, yields easily without sparking or fracturing. Chalcopyrite, 3.5 to 4, though close in hardness, resists deformation and leaves a dark, greenish-black streak on unglazed porcelain. Mica leaves no streak and often breaks into sheets. When in doubt, a streak plate and a hand lens are worth their weight in clarity. Beyond field tricks, there's a psychological trap. The visual excitement of a promising glint can cause prospectors to oversample worthless material. Buckets of hot rock concentrates from creek beds around Castell and Honey Creek have turned up nothing in lab tests, despite appearing auriferous in hand sample. In almost every case, the culprit was oxidized chalcopyrite or decomposed biotite matrix. These disappointments aren't trivial. They burn time, resources, and morale. To avoid the spiral, experienced prospectors build in control tests early. From every promising site, they'll isolate one pan of material and perform all diagnostics before scaling up. No color without crush. No glint without gravity. These rules protect against false positives and help focus effort where the real gold signals lie, especially in zones that combine quartz, iron oxide, and heavy mineral clustering. But to make these field decisions reliable, the next step is standardizing your tools and workflow. Prospectors across Texas are increasingly relying on a consistent field kit that lets them triage material fast, test on site, and log results systematically. From mesh sieves to flashlights and magnet sweeps, this core setup has become the foundation of efficient, evidence-based gold hunting in the region. Efficiency in the field starts with precision, and in Texas, where mineralized ground is often subtle and dispersed, a refined field kit isn't optional. It's essential. The most successful prospectors aren't necessarily those who hike the furthest, but those who carry the right tools to make every test count. Over years of trial and error, a consensus has emerged across the hill country. A compact, durable, and repeatable setup that allows gold and quartz evaluation on site, without lab dependence. At the heart of this kit are classification sieves, typically number 20, 0.85 mm, number 30, 0.6 mm, and number 50, 0.3 mm mesh. These allow for consistent sampling by removing oversized waste and separating concentrates into workable fractions. In dry or wet conditions, sieving reduces guesswork, ensuring that flour gold isn't lost in gravel or overwhelmed by organics. In the Llano area, for instance, field teams sieve directly into sealable sample bags, preserving both grain size and location context for later testing. Next comes the loop, usually 10x or 20x magnification. This tool is indispensable for distinguishing gold from mica, inspecting fracture faces in quartz, and spotting cubic pyrite or limonite texture. A loop also reveals surface features that suggest multiple mineralization episodes, such as overgrowths or microveinlets within larger quartz chunks. It transforms what looks like a blank rock into a readable map of mineral history. Magnets, particularly neodymium, serve both as tools of detection and exclusion. By sweeping dry concentrates or bedrock cracks, a prospector can isolate magnetite, ilmenite, and even hematite fragments, common companions to gold. More importantly, areas with high magnetic response often correspond to upstream iron-rich veins, acting as pathfinders toward hydrothermal zones. A magnet in a zip-top bag, also allows for clean retrieval without contaminating hands or sample material. For rapid mineral testing, a small bottle of vinegar or dilute hydrochloric acid provides immediate feedback on carbonates and surface oxides. While it won't touch gold or quartz, it can fizz on calcite or limonite-coated surfaces, clarifying whether the orange staining is truly iron oxide or just sediment. Combined with a porcelain streak plate, this allows for quick differentiation between pyrite, chalcopyrite, and non-metallic imposters. Lighting is another overlooked asset. A compact, high-lumen flashlight, preferably with adjustable intensity and beam angle, helps read quartz luster, inspect crevices, and detect hidden color zoning. Many serious fieldworkers also carry UV flashlights, long-wave light that can induce fluorescence in certain minerals, though not definitive for gold, can suggest alteration zones, e.g. scheelite or calcite veins in contact zones. Finally, all of this is grounded by sample control. A waterproof field notebook or GPS-enabled smartphone logs site coordinates, mesh size, observed traits, and preliminary impressions. Each bagged sample gets a unique code, no exceptions. This system enables later cross-referencing between visual traits and assay results, revealing patterns across regions and guiding future expeditions. With these tools, Texas prospectors convert guesswork into structured investigation. But tools alone aren't enough. Understanding how minerals behave during concentration, how they settle, separate, and align in a pan, is the next skill that separates promising sediment from real pay dirt. And in gold-bearing creeks, one invisible line often divides profit from disappointment: the density split. In every gold pan, there's an invisible boundary, a line where gravity begins to reveal the truth. This density split is what separates casual sediment from concentrated potential. And in the mineral-rich but erratic zones of central Texas, reading this line correctly determines whether a site holds promise or just a mirage. It's not just about spotting gold. It's about understanding where gold should be settling in relation to other dense minerals like magnetite, garnet, galena, and hematite. Gold, with a specific gravity of 19.3, is far denser than nearly everything else in the pan. It should settle lowest, hug the bottom crease, and resist motion even under aggressive swirling. Just above it, magnetite, 5.1, and ilmenite, 4.7, form a heavier black sand band. Garnet, 3.5 to 4.3, typically red or brown and subrounded in Texas placer samples, forms a distinct line above that. Once you know what these layers look like in motion, their order becomes diagnostic. If black sands dominate, but gold isn't appearing below them, the source may be poor or improperly sampled. Field testing this density gradient requires careful panning technique. Skilled prospectors load no more than a half pan, remove light overburden with broad swirls, and begin isolating heavies using short, controlled taps that draw dense material into the bottom crease. Then, by slowly washing off lighter grains layer by layer, the lines of separation appear, almost like a geological barcode. Deviations from expected patterns often indicate contamination or mixing of layers during collection. Some prospectors go further, using mini sluices or gravity traps in the field to capture and sort these minerals across riffles. In Texas, where flow can be inconsistent, recirculating water systems, battery-powered, allow these tests to proceed even in dry gulches. By analyzing which minerals appear in which riffle zones, one can estimate whether the gold is flower size and free milling, or coarser and likely sourced from nearby veins. When dense bands show clean separation and gold holds at the deepest point, confidence rises. One often overlooked indicator in Texas panning is galena, lead sulfide, with a specific gravity close to 7.6. Though not widespread, when present as small cubic grains, galena often co-occurs with gold in hydrothermal systems and can flag sulfide-rich targets. because it has a silvery luster and resists corrosion. It may survive long transport and show up in pans far from its bedrock source. False positives do occur. Decomposed schist, mica fragments, and plant debris can cluster and mimic heavier materials, especially when organic oils from roots or bacteria are present. That's why experienced field workers clean pans and tools regularly and perform magnet sweeps before final settling. If magnetics dominate the bottom, but no gold appears beneath them after repeated tests, it's a red flag for misreading the density line. Understanding the split also informs upstream tracing. If gold settles consistently below garnet and magnetite in multiple downstream test sites, but not above a certain point, the prospecting window narrows. By walking back until the pattern breaks, prospectors can isolate the upstream reach where gold exits the system, often pointing directly to a hidden or subparallel quartz vein. But not every quartz vein is worth pursuing. In Texas, hundreds of them snake through the terrain, and only a small fraction carry significant gold. Knowing which veins deserve your time means going beyond appearance and learning the geometry, chemistry, and behavior that distinguishes a rich system from a sterile one. Quartz is everywhere in central Texas. It spills from road cuts, fills creek beds, and laces across schist outcrops in pale, brittle seams. But the overwhelming majority of it is sterile, formed during periods of low mineral transport or outside the thermal window for gold deposition. For prospectors, the key isn't finding quartz. It's knowing when to break it, sample it, or pass it by. In the Llano Uplift, this distinction hinges on vein width, strike continuity, sulfide presence, and host rock context. The first and most immediate filter is vein width. While thin stringers under 2 centimeters can signal mineralized systems, they rarely carry recoverable gold on their own. Productive veins in the pack saddle schist zone, for instance, typically range from 5 to 25 centimeters in width, often with evidence of repeated fracturing and silica deposition, seen as internal zoning or layered textures. Veins that heal and reopen, indicated by cross-cutting quartz generations, are more likely to host metal transport events. Next comes strike length and continuity. A quartz vein that runs for several meters in a consistent direction, particularly if it follows a known fault trend, deserves closer scrutiny. In the area south of Castell, productive samples have been found in veins trending northeast-southwest, roughly parallel to known shear zones. Field mapping with a compass and inclinometer allows prospectors to trace these veins and look for consistent thickness, wall rock alteration, and structural traps like folds or flexures where fluids may have pooled and cooled. Sulfide presence is a stronger clue. Quartz veins with visible pyrite, chalcopyrite, or even oxidized sulfide staining, limonite halos, manganese smears, are prioritized for sampling. Gold often follows sulfide pathways, and even when the sulfides have long since weathered out, their oxidized residues remain. In one documented case near Valley Spring, a heavily iron-stained quartz vein less than 20 centimeters wide yielded 0.8 G of gold after crushing and gravity concentration, despite no visible metal. The giveaway? Limonite boxworks, hollow cavities where sulfides once crystallized. But perhaps most decisive is host rock context. Quartz intersecting amphibolite, chloritic schist, or biotite gneiss has a higher chance of mineralization than quartz in pure granite. These metamorphic rocks often carry the trace elements and permeability required for gold-rich fluid deposition. Prospectors use this filter aggressively, often ignoring quartz unless it cuts reactive or foliated host material. On some tracks west of Llano, entire ridgelines of granite-hosted quartz have been dismissed, while nearby schist-bound systems continue to yield assayable gold. The actual sampling process follows a set sequence. Promising veins are chipped with a masonry hammer or small chisel, preserving both quartz and adjacent wall rock. Samples are labeled, bagged, and crushed later for panning or specific gravity separation. Some teams also collect float samples downslope of exposed veins, testing whether erosion has concentrated fines in nearby creeks, an early indicator of economic viability. They left behind rock piles, rusted cans, and broken picks, remnants of Depression-era mining across central Texas. But they also left something more valuable: tailings. And in a quiet shift over the last decade, modern prospectors have begun uncovering real gold. Not from untouched veins, but from the discarded material of previous generations. This unexpected revival challenges assumptions about what worked out means and opens a new chapter in small-scale Texas prospecting. In the 1930s, under federal gold price controls, many small operations sprang up in Llano, Mason, and Gillespie counties. These miners lacked precision equipment, often relying on mercury amalgamation or rudimentary gravity separation. As a result, their tailings, piles of crushed rock and sluice discard, frequently retained significant gold, especially the fine material they couldn't recover. In multiple verified cases, tailings tested today yield between 0.3 and 1.1 grams of gold per ton. Numbers low by industrial standards, but viable for selective hand recovery. The first step is locating these sites. Many tailings are partially buried, their surface indistinguishable from native soil. But clues remain. Prospectors look for unnatural mounds with angular quartz fragments, often bleached or oxidized, and sometimes aligned along creek benches or slope contours. In the Sandy Creek drainage, just south of Babyhead Mountain, several of these low-profile tailings fields have recently been reworked, yielding gold-bearing concentrates after careful classification and panning. Testing tailings requires a shift in method. Unlike virgin ground, tailings are already crushed, but inconsistently. This makes classification by mesh essential. A standard number 20 sieve isolates most recoverable fines, while a number 50 catches flour gold embedded in finer matrix. After classification, dry panning or recirculating systems are used to assess density splits. Tailings gold tends to be flat and fine, easily lost if rushed. A magnet sweep often reveals associated magnetite and iron oxides, validating the original deposit's mineralogy. One major advantage of reworking tailings is access legality. In many cases, these piles sit on private ranch land, far from modern mining claims. With landowner permission, prospectors can operate with minimal environmental disruption, using hand tools only. Some have formalized agreements, access in exchange for cleanup, erosion control, or percentage of recoveries. This cooperative model is gaining traction as ranchers recognize the potential value in forgotten waste. But there are challenges. Some tailings contain mercury residues, a legacy of early extraction methods. Any glistening silver flecks or oily film during panning must be treated with caution. Proper gloves, disposal containers, and sample testing can mitigate risk. Where mercury is confirmed, recovery should be halted unless done with certified equipment and safety protocols. These zones may still hold research value, but require specialized handling. Surprisingly, some tailings outperform the surrounding veins. In one 2023 case near Loyal Valley, reprocessed tailings yielded consistent 0.7 g/ton results across 12 samples, double the returns from nearby quartz still embedded in bedrock. The likely cause? The original miners stopped when visible gold ran out, not realizing how much remained as fines. Today's tools recover what there's missed. This realization flips the logic of exploration. If value can be extracted from waste, then priorities change, from chasing new ground to verifying old discards. But it also raises a key question. How do you decide when it's time to assay, and when a visual or gravity test is good enough? The answer determines both strategy and budget, and defines how deep a prospector should go. You don't always need a lab, but when you do, it pays to choose wisely. In Texas prospecting, knowing when to invest in a fire assay versus relying on visual indicators or simple gravity separation is one of the most cost-defining decisions a prospector makes. Done too early, and you waste money on non-starters. Done too late, and you miss a narrow opportunity window. Whether to stake, sell, or scale, the logic behind this choice is as technical as it is practical. Fire assays remain the gold standard for quantifying metal content, especially in low-grade, fine-dispersed material. But each sample can cost $40 to $100, depending on lab, rush timing, and prep complexity. For this reason, Texas fieldworkers often apply a tiered approach. Initial screening relies on visual plus field test logic. Is the material from a favorable host? Does it pass the weight, fracture, and density tests? Are there sulfide indicators or oxide staining? Has the panning yielded consistent fine gold over multiple points in a drainage? If the answer is yes to 3 or more of these, the material may justify bench scale testing. That step involves crushing and concentrating several kilograms of material, then recovering a visible fraction by gravity, e.g., blue bowl or spiral wheel. If that fraction totals more than 0.2 grams per kilo, and if the host quartz shows consistent mineralization, a fire assay becomes justifiable. Not to prove gold exists, but to quantify its grade and economic potential. Certain situations, however, demand assays up front. If the gold is microscopic and consistently invisible in concentrates, even after gravity testing, but sulfide presence is high, then the system may be refractory. Gold locked inside pyrite or arsenopyrite. In these cases, only a fire assay with proper roasting or aqua regia digestion can reveal true value. Central Texas veins cutting into chlorite schist zones sometimes produce exactly this profile. No visible gold, but assays returning 2 to 3 grams per ton. Other cases do not require assay. When visible gold appears in pan or quartz, especially in flakes or wire form, its presence is self-confirming. Instead of paying for lab work, smart prospectors invest in repeatability mapping, grid sampling the surrounding area to trace the consistency of values. This approach, collecting 10+ pan samples at fixed intervals, helps determine whether the visible gold is a fluke or part of a broader zone. Only after pattern confirmation is assay considered, and only on composite samples. A middle ground exists in specific gravity bottle tests, a DIY method where the difference between dry and water-submerged weight reveals density. This is particularly effective for coarse concentrates and can provide a rough estimate of gold content without full lab analysis. Some Texas field teams also use digital scales and hand-milled concentrates to compare recovery ratios by volume, creating local benchmarks that inform whether lab testing is even needed. But when assay is chosen, chain of custody and documentation become critical. Samples must be bagged, labeled with location and context, and ideally split into retainable portions. Labs prefer 300, 500 G per sample, and will often ask for matrix description, whether the sample is oxide, sulfide, or silicate dominant. Including field notes improves accuracy and credibility, especially if results are later used to attract partners or buyers. Knowing when to assay sharpens strategy, but value isn't always in raw gold. Increasingly, collectors are paying premiums for gold-bearing quartz specimens with distinct mineral matrices, especially those with iron, manganese, or chlorite associations. These pieces bypass refinery prices entirely and enter a different market. Understanding what today's buyers seek can reshape what material you keep and what you sell.